Morning everyone. So today I want to introduce to you another really common chemical technique known as spectrophotometry. What we have here on the left hand side here is a light source. You can toggle this light source here on and off using this red button. This light source here that we're going to be sending in is going to pass through an aqueous solution. If I can track how much of this light here actually passes through the sample, we have a detector on the far side here. That value is known as the transmittance. I can toggle this reading back and forth between transmittance and absorbance here. Absorbance, as the name suggests, is how much of this incident light here has actually been absorbed by the chemicals passing through this cuvette here. Because in spectrophotometry here, we can actually control which particular wavelength of light to actually send in. Right now here, we're sending in a green colored laser beam here, and that one here has a preset wavelength of 508 nanometers. We're going to find that different chemicals will have a different preset value. We can actually figure out how they got this preset value, but if you want to actually play around with which particular wavelength to actually send in solution, you just click this variable button, and this one here will actually allow you to change. In the visible spectrum here, we can go all the way down from the sort of 300, 400 side here, the blue purple wavelengths, all the way up to the 700 side, which is more the reddish wavelength. What we can play around with is the solution itself. Every chemical will have a very specific color that it absorbs best. So they start off just with a drink mix solution here. They picked about 7 or 8 other chemicals here, sort of ranging the colors of the rainbow here. These chemicals are actually these colors. You'll notice what they have in common is they actually are all solutions of transition metal ions. So from our periodicity chapter here, you should be able to explain to me how come these ions are actually colored in solution. What we're going to do is we're going to specifically investigate cobalt-2 nitrate as well as cobalt-2 chloride. These solutions here are showing red. Remember, if a chemical here shows red, it's not because it actually absorbs red. Red is just a complementary color that's transmitted through. In fact, it's actually the opposite color on the color wheel that's actually being absorbed. So you can toggle between different chemicals using this bar here. When you've actually chosen a chemical here, you can actually play around with the concentration. Right now I'm in units millimolar here. It gives me a range sliding it down to 0 concentration. So that's when I have no cobalt nitrate in solution, or having dissolved enough, I can make it steadily more concentrated here all the way up to 400 millimolar for this one. That also is going to influence how much the light actually gets absorbed. We can play around with one other thing here in this virtual environment. Usually this piece of glassware here is called a cuvette. The light usually passes through 1 centimeter deep worth of solution. Evidently, as it passes through like more and more chemical, if I'm going to absorb light, more of that light is actually going to get absorbed. In this virtual environment, we can actually play around with the width. We call this the path length that the light actually travels through here. I can make this width here a little bit shorter, or I can make this cuvette here almost double the length here. As it tries to pass through twice as much chemical here, that is going to have a response with absorbance and transmittance as well. Another way of doing that here, although we're not going to do this in real life, you can actually play around this detector. You can actually move this detector here inwards. That would equally well change the path length. We're going to try to mimic what it looks like in real life, so we're going to keep our detector on the far side here. We're going to be back at 1 centimeter deep, and we can actually measure how long of a path length the laser light is actually traveling through to actually track the change in length. So we're going to do this experiment here in 3 parts. Let me just reset the solution so it's a little bit cleaner. We're going to start off looking at a cobalt-2 nitrate solution. They already show me that it's a red color. I'm going to leave it at the default setting of 100 millimolar right now. We're going to turn on the light here. First one we want to investigate is how did they know to preset the wavelength at 540? We're going to find that as you toggle to other chemicals, the preset is actually different. So the first part of this one here, we're going to start off with variable. We're going to send in our laser light here, and this one here, it's going to seem a little bit tedious. Most spectrophotometers would do this automated for you, but I want to give you a feel of what the spectrophotometer is actually doing. We're going to take down how does your absorbance or transmittance change as I change the wavelength. So I'm going to start off on the one end here. I believe it's 380 nanometers here. They even animate here 380 would be the sort of purplish violet side here. So we have 380 nanometers here. I'm going to record down as it travels through that 1 centimeter cuvette. The transmittance reading is 92.90. I'm going to toggle back and forth here with absorbance. I'm going to record down the absorbance reading. We'll notice the solution here happens to transmit purple light here very, very well. You notice that that corresponds with a very low absorbance. So transmittance and absorbance should be inversely related. The more that gets through, the less that actually gets absorbed. Now, technically here, if I had a lot of time, I can actually test, well, for every 1 nanometer at a time here, how does this absorbance reading change for every exact nanometer? I don't have the time for that. So what I'm going to do here is I'm just going to roughly, since I'm starting at 380, since I can get up to 780, I'm going to roughly go up in 20 nanometer increments. There's nothing special about this 20 nanometer. You could have gone up in 30s, you could have gone up in 50s, no matter what. But the 20 here seems to give me enough detail here. So what we're going to do, we start at 380, take down the transmittance reading, toggle back and forth between the absorbance reading. I'm going to try to move it over to 400, and then same thing. Take down the absorbance reading, take down the transmittance reading, go across here, just every 20 nanometers here, take down absorbance and transmittance, and then I can investigate how does the absorbance or transmittance depend on this wavelength. How did they actually figure out the preset for this particular chemical? That's part one. Part two, once you actually figure out what the preset, what the special wavelength for each chemical is, every chemical will have its own, we call that a lambda max, the lambda where the absorbance is actually the highest, that gives you the strongest signal. We're going to track down how does your absorbance change versus your concentration. So I'm going to start off with having, let's say, 0 concentration. I'm going to go upwards. Again, technically, you could do any millimolar you want here. I'm going to go up in increments of 100. So at 100, what is it? At 200 concentration, what is it? At 300, so on and so forth. And then lastly, in part 3, we're going to play around with the path length. So we're going to start off having a path length of about 0.5 centimeters, take down 1 centimeters, take down 1.5, and take down 2 centimeters for that chemical to sort of investigate how absorbance changes based on what we're looking at. Right? So we're going to mainly focus on cobalt nitrate. There is one part I'm actually going to compare. While cobalt here is in the +2 oxidation state, we actually have another solution here, cobalt 2 chloride. You'll notice that it's a little bit lighter color. But we're going to see, well, both of them are actually cobalt +2. We're going to see if the lambda max is actually different between these ones. So as we track our absorbance spectra, as we try to figure out the preset wavelength for these two solutions, I'm going to want to figure out whether the curves look similar or they look different, why or why not. Okay? So I'm going to assume that you've done that here. Again, I'm going to reiterate here. Part 1, I'm going to have a chemical here. We would have defaulted here at 100 millimolar. We're going to start off here having path length of roughly 1 centimeter. For a fair test, I want to make sure I'm only changing one variable at a time. So part 1, when I have everything sort of at default settings here, I have my cobalt nitrate, it's 100 millimolar. I'm going to change the wavelength here every 20 nanometers, and I'm going to track how does transmittance and absorbance change. I'm going to compare that to a cobalt 2 chloride solution, same thing, absorbance versus wavelength. Once I find the nice preset wavelength for that particular chemical, I'm then going to play around with the concentration, from low concentration to high concentration. How does the absorbance reading change? And then lastly, how does it change as I change the path length? Okay. So I've actually taken down these readings already here. I'm going to pull up my Excel spreadsheet here and we'll see what we get. Okay, so just showing you my Excel spreadsheet here. Again, what we're going to do first is we're going to examine part 1. How does the absorbance of the solution change as I change the wavelength that's being sent in? Again, there's nothing magical about me going up in 20 nanometer increments. You could have gone up in whatever increments you wanted. Excel is actually fairly clever here. If you give it a couple wavelengths to start off, let's say 380, 400, 420, what you can do here is you can actually highlight. Excel will actually track the pattern between these numbers. It will actually know, oh, these numbers here are actually off by 20. You can take this lower right-hand corner with this green corner here, and you can actually drag this all the way down here. We want to go all the way down to 780, and it actually plot those numbers for you here. So on the simulation, what I would have done is I would toggle it to 380. I would record down the absorbance reading for the cobalt nitrate solution at 100 millimolar as we were doing it here. This absorbance here was actually 0.03. I would press the percent transmittance button, and I would also record down the percent transmittance as well. So for example, the transmittance for that button was 92.90. And then what I would do is I would slide the wavelength over, change the color of light that I'm actually sending in. It would be already on percent transmittance. I'm going to record down that number. It says 99.54, and I'm going to record down the absorbance and basically go your way down this procedure here. Just to save us a little bit of time here, that's essentially the procedure I did going all the way through. I've already done that for you for the absorbance readings. Okay. So in general here, when you have a spreadsheet, when you're plotting a graph, we always want to have the X column first. So I want absorbance versus wavelength. That's why my wavelength here is down the X column here. I'm going to see what this graph here is looking like first. You want to highlight your X column and your Y column here. as you go up under your Insert tab, you can actually insert many different styles of graphs here. You may be tempted right now here to plot it as a 2D line graph. In general, I try to encourage people, even if this one here does end up as a straight line, I'd encourage you to actually, instead of using this 2D line graph, instead use a scatter plot. What a scatter plot is going to do is it's going to take this one here as an x-coordinate, y-coordinate, put a point. Next point here, x-coordinate, y-coordinate, put a point. And basically it's going to plot all the dots for you. I can always come along and I can add the trend line afterwards. So I'm just going to click the one here, scatter plot here, that just has all the dots. Excel understands that it's x column and then y column. We're going to just click one of our quick layouts here that I can actually change the axis titles, and therefore I can actually play around with the titles. So remember, our titles here should always be y versus x. So this one here is absorbance versus wavelength. We have our y-axis title here. I'm going to put that as absorbance. Absorbance is actually the logarithm of the light intensities actually being absorbed. So this one here actually has no units. For wavelength down here, wavelength, I'm measuring it currently in nanometers. Right? Sometimes it will have different series labels if I have multiple different plots on the same graph. This one I only have one, so I'm just going to delete that one off. Okay. So my graph is already looking fairly nice. Again, spectrophotometers here very often would just automate this procedure for you. It can even sense in real time, as I send in all these wavelengths here, how does this particular chemical actually respond? Depending on the particular chemical, it will have a very unique wavelength that has max absorbance. That particular wavelength here, we're going to call it a lambda max. Because I just roughly went up in 20 nanometer increments here, I seem to have a maximum here. But maybe sort of in and around this one here, maybe it actually gets a little bit higher, a little bit lower. You don't really need to get the really highest point. You just want to roughly get the highest absorbance so that it gives you the strongest signal for the rest of this lab here. So what I've done here is I'm noticing here that somewhere between maybe 520, 560 or so, it seems to be peaking at absorbance of about 0.45, 0.46 or so. I roughly went up in 20 nanometer increments. What I can do is I can go back and I can say, well, let's get some of the detail. At 540, it was 0.44. What would it be at 542, 546? You can actually go back and actually look at some more detail. So what I'm going to do here is I went back in exactly that fashion. You don't even need to put them in order. So in this case here, my 542, I went back and actually tracked down the absorbance reading was actually 0.45. I went 549. That was actually the preset that they gave me. The preset is actually that lambda max. Lambda max is the wavelength that actually gives you the highest absorbance. I also tested at 555, roughly speaking here. So 555 here had absorbance reading of 0.47. Okay. So what's going to happen here is as I try to extend my graph here to include those points, again, it's just going to plot x-coordinate, y-coordinate. I know they're out of order. That's fine. What we're going to do here, I'm just going to drag, hopefully, this purple line here. And I can drag it so it knows x-coordinate, y-coordinate. It's just added a couple more points. It's just giving me a little bit more resolution there. Maybe there was one that was even higher than the 0.46 that I was looking at here. That just gives me a little more detail. These chemicals here are colored, so I would expect within the visible region there is a color that's being absorbed. This time it's absorbing like a 540, 550 wavelength or so. The opposite color, the absorbed color here is like a greenish color or so. The opposite side is actually more so a red color, which is what we end up seeing. Some chemicals will actually show more than one peak. You just want to choose the one that gives you the strongest signal because that'll be the easiest one to work with later on. So that pretty much here is part one. For this particular copper nitrate sample at 100 millimolar here, we've just scanned through the different wavelengths. We wanted to find our lambda max, which is actually what they preset as their wavelength. What I'm going to do here is, because we also did wavelength against transmittance, what I did is I just copied down the wavelength, again 380 all the way down here, the transmittance readings instead. Again, when the absorbance is high, the transmittance is low, and vice versa. You'll notice between here, the 400 to the 700, 800 or so wavelengths here, I've already labeled the titles and graphs for you here, where in the absorbance graph here, where we end up peaking, most light is actually being absorbed. That corresponds with most light here not getting through. So that sort of makes sense to you here. Although absorbance here typically gives you a more linear trend later on, that's why absorbance is the preference over looking at it with transmittance. If you actually did this procedure in detail, you actually find that for this particular chemical, it actually stays at 0.47 for quite a while. Maybe percent transmittance would give you that resolution where even though your absorbance may be the same, the transmittance might dip a little bit lower. We want the point when the transmittance is lowest in order for us to find the lambda max, the wavelength that gives us the highest absorbance. So that's part one. We've done a absorbance spectra here. We actually figured out the preset wavelength should be 549. Now what I'm going to do is I'm going to set it at that preset wavelength, and I'm going to investigate how does my absorbance change. Part two is going to be how does it change via concentration, and the other is going to be with path length as well. Just before we get to those two graphs here, I forgot we had one other graph. What I've done here is I've roughly gone up in the 20 nanometer wavelengths again. This is the same cobalt nitrate data that we had. Because cobalt is also in the same +2 state here, I've also tracked down for that chemical here what are its absorbance readings here. As long as you put the X column first, if you want to plot two other graphs here on the same plot, you just highlight all three columns all at once. Excel will understand that this is your X value, your independent variable, and it's going to plot two sets of values here, all these Y values as one series, all these Y values as another series. So again, under your insert tab here, we'll plot them as a scatter plot here. You can change the titles and all that there, and you actually realize there, okay, well, our first solution here was this sort of blue style graph here. My other chemical, the cobalt chloride, also cobalt in the +2 oxidation state. You'll notice the concentration were actually the same, but depending on what else is in solution, maybe the ligand concentration is actually different. Maybe the actual absorbance in solution would actually be different, but you notice there is no shift of lambda max because we are both cobalt +2, the preset wavelength is actually the one that gives me the strongest signal, whether I was looking at the nitrate ligand or the chloride ligand. Okay, so back to part two as I was mentioning here. Now that we know what the preset wavelength is, I'm going to set my laser light to send in 549. I'm still going to be at 100 millimolar for now, and then what I'm testing in part two is how does the absorbance change relative to concentration. Again, what I've done here is I've just roughly gone up. It maxes out between 0 and 400. So what I did is I just went up in 100 nanometer increments here. I've already set up this graph here to plot the graph directly as I plot the numbers in. So let me just track these numbers for you. I had recorded these numbers earlier. At 0 concentration, I don't expect anything to absorb. The absorbance is 0. So I do have that 0 point, no problem. When I slide the bar here to 100 millimolar, where it was initially, this one here was actually 0.47, which matches what we had earlier. It plots the point for you there. At 200 here, I tracked it again. This is 0.94. I'm only tracking absorbance here. At 300, 1.42. And at 400, this is actually 1.89. All right. So it's plotted this graph for us here. Right away, we see from this trend here, we're getting a nice linear correlation. This is getting us the start of what's referred to as the Beer-Lambert law. We'll summarize it towards the end here. Even though this one here would have ended up as a straight line, I still plotted it as a scatter plot. If I want to add the trend line afterwards, I just click the dots here. I'm going to right click. I'm going to add a trend line. The trend lines here, mostly in high school, our trend lines are actually just straight line fits. So you can do a linear fit here. If it ends up being a curve, maybe you do a polynomial fit for other graphs here. What I'm going to do is I'm going to display the equation on the chart. This one here actually gives us a really nice correlation here. We actually refer to this absorbance concentration graph as a calibration plot because I took a pure sample cobalt nitrate. I sort of diluted it down to these concentrations. I tracked down the absorbance, and now I have an equation that links. If you have something that has an unknown absorbance, I can look at this calibration plot and actually figure out what the concentration actually is. So this equation will be very useful for us. We can even display something called an R-squared value. An R-squared value here matches up how do your dots here match up to your best fit line. Is it really linear? The closer it is to 1, the nicer the linear fit is. Right now here, this is spot on 1. Basically, all my dots here perfectly land on the graph. So as I mentioned here, this is called a calibration graph. Let's say I now take an unknown sample. Let's say I have a reaction and then creates cobalt nitrate, but I don't know how much cobalt nitrate is in there. Once you've plotted a calibration plot, you'd stick it through a spectrophotometer. I may not know the concentration, but the spectrophotometer here might give it you, oh, my unknown actually has a absorbance of 1.20. Well, absorbance here is the y-axis. If I have 1.20 in for y, I can just solve through this here, take 1.20. I'm going to add the y-intercept, so add 0.002, divide it by my slope, 0.0047, and there. we've gotten the concentration is roughly 256. So yet another way for us to track the concentration. Evidently, it's nicer if your calibration graph is a nice wide range so that your unknown is going to be somewhere within that range. What if I had something different? What if I had some unknown here, the concentration was actually 60? What absorbance would I expect for it? Again, now the unknown is going to be the horizontal side here. So we're going to go 0.0047 times it by 60 millimolar minus 0.002. I would expect the absorbance reading to be 0.28. We can look at the graph there, and we're going to see here, when the concentration is 60, we see that the concentration absorbance is actually 0.28 or so. All right? So that's a nice start to Beer's law. The third part here, we want to investigate same solution. I want to keep most things constant, the same preset wavelength, the same concentration, same chemical, same everything. But with the magic of a virtual lab, I'm going to actually play around with the actual path length that the light actually goes through. So it actually maxes out between 0.8 to 2.0. Again, I've set up the graph here, already labeled for you here, and it can actually plot the numbers directly. So we're going to go at 0.5. I recorded these numbers down earlier. If you slide the PhET over, it was 0.24 of absorbance. At 1, it was 0.47. At 1.5, it was 0.68. And then at 2, it was 0.94. Again, nicely, based on Beer's law here, it ends up being a nice straight line. I still plot it as a scatter plot, a nice XY sort of axis here. Click the dots here. Right click, you can add a trend line. I'm going to add a linear trend line, display the equation, display the R squared. Again, the equation will be useful if you happen to know a particular path length. The chemical is exactly the same molarity. It's the same laser light that I'm actually passing through, but because it's passing through more of the sample, it has more opportunity to get absorbed. The absorbance gradually increases, and there again is an equation that links absorbance with length. R squared value, like I mentioned, the closer it is to 1, the closer your dots actually land on a perfect straight line fit. And in this case here, some of the dots here are a little bit higher, a little bit lower. 0.9982 here is actually very, very linear. All right. So based on this lab here, we can actually have support for what's referred to as Beer's law or the Beer-Lambert law. And what it says here is at really low concentrations, your absorbance in the aqueous solution is proportional. This epsilon symbol here is called the molar absorptivity. That one there is going to be a constant depending on the chemical that we're looking at. But you see that it's proportional. Absorbance was linear when I changed the path length, keeping concentration the same, or keeping the path length the same here. As I change concentration, the absorbance would also differ as well, linear. This Beer-Lambert law only works for really low molarities. As you get concentrations that are too high, light ends up scattering off the cuvette, and it ends up sort of deviating from this Beer-Lambert law. Okay. A couple other things I want to just introduce to you while I have it on the board here. Sometimes you might be interested, as you look through a long set of data, you might want to really quickly find your maximum value, really quickly find your minimum value. Just a little spin-off here. Let's say I wanted to, at a glance, which one here is the maximum. Excel is actually pre-programmed in with some common functions. So what I can do here is I can start off with that equal symbol. I can tell Excel the next thing I'm going to type is actually a formula. I can actually use the maximum formula. It's actually telling you here, it's going to return in a set of values which one is the biggest. I'm going to put a bracket around, and I'm just going to highlight over between these values here, which one's the biggest, and right away it's known. Okay, 0.97. If, in contrast, for whatever reason, I might want to know a minima, let's say it's transmittance here. Start off with the equal again. I'm going to use minima as a function here. We're going to minima. Again, I'm going to highlight over what's the minimum of those numbers there. This would be useful, especially when I have a really long set of data here. In this case, I only have 4 data points here. It really doesn't justify why I might need to do that. So that's the maximum formula. What's the minimum formula? Especially if I did this in real life, maybe there's always going to be some random error associated with this. So let's say I took down this reading here a couple times. Let's say at 2 centimeters here, the first time I got 0.94, second time I got 0.92, last time I got 0.97. Right? That random fluctuation equal in both directions is sort of not surprising to me. What we can do here is we can take an average before we actually plot that number. So we can actually, again, use one of Excel's other preset formulas. Again, start off with equal. You can do it one of 2 ways. You can start off, well, how do I take an average? I want to sum up a few numbers. You can obviously go this plus this plus this. Excel is actually pre-programmed with the sum formula here. I'm going to sum up these guys here, and I'm going to close that bracket. It knows to add up those numbers, and I'm going to divide it by 3. because I know there's 3 numbers going into it, I'm going to be a little clever here. I'm actually going to use Excel's count function. And the count function, as you can read here, it actually is counting the number of cells that actually contain numbers inside. So if I also do the count function, I also overlay these functions here, it's actually going to say between B128 and D128, how many of these cells are actually filled in? Well, I have 1 number, 2 number, 3 numbers. It'll automatically divide by 3 for me. Why might I be interested in doing that here? Let's say I end up deleting off one of these values here. Well, let's see if the formula is still giving me what we want. This is still adding up. This B128, it's adding this one here as a 0, it's adding this one. If I had divided with a static 3, it would now be off because I only have 2 numbers going into the average. So just to avoid that here, what we can do is we can actually use the average formula. So average is a very common thing that we use on spreadsheets here. Again, you just highlight over the set of data that you're interested in. I want to take the average of those numbers, and there we go. We got the average 0.955 again. Okay. So just for your reference here, I'm just going to show you what formulas did I use. I used an equal maximum formula to get the maximum number. I used an equal minimum formula to get the lowest number. I used the sum formula if you're interested in adding numbers. I used the formula count function. So that counts how many cells actually have something inside of it. And then I also use the average formula. It has way more formulas than that, but those are some of the most common ones that we're going to end up seeing. See if you can pick another chemical for yourself, take down some of these readings here, try to calculate a molar absorptivity for yourself, and that one there is actually going to give you the proportionality constant. Absorbance has no units, so length is centimeters, concentration is, in this case here, millimolars, so the molar absorptivity in this case has to get rid of the centimeter, so it has to be a per centimeter, and also have to have a per millimolar for canceling out concentration, leaving you in absorbance with no units. If you have any questions, just let me know. Thanks, guys.